Good morning, everyone. My name is Walter Silima. I'm a second year master student at the University of the Western Cape. I'm working with Prof. Matia Bakari, Dr. Fanshia Ann, and Mr. Islam Hussein. We are working on machine learning approaches to study star formation and black hole accretion in the mighty survey. The aim of our work is to implement and optimize supervised machine learning algorithms so that we can accurately classify between star-forming galaxies and active galactic nuclei. And this is motivated because astronomy is currently faced with the huge increase in the amount of data in terms of the volume of data and also in terms of the number of sources that they are detecting per survey. And the currently manually applied techniques to classify the two sources will not be effective. We focus on the radio continuum, which is mainly dominated by star-forming galaxies and active galactic nuclei. Star-forming galaxies are galaxies with a high rate of ongoing star formation activity, while AGN, active galactic nuclei, is the compact region at the center of the galaxy with at least some non-stellar luminosities over some parts of the electromagnetic spectrum. On the figure on the left, I show an andromeda, which is star-forming galaxies in different wavelengths, and similarly on the right, I show the closest directly around AGN in different wavelengths. So we are using supervised machine learning, and I'm trying to show an architecture of how supervised machine learning algorithm works. A supervised algorithm, you need a training data that is labeled, and you will then need a test data to evaluate how well the algorithm is doing. I show my label data as an example of properties of triangles and circles, and my labels should be to indicate which properties are triangle and which are circles. You then take this data, you feed it into a model, and this is called model training. So the model is going to figure out the relationship between the properties of the two sources and the labels, and then it will memorize that relationship. And then you then take the unseen test data, you feed it to the model, and then the model should be able to tell which one is a triangle, which one is a circle. We adopt 5 supervised algorithm, which is logistic regression, support vector machines, k-nearest neighbor, random forest, and XGBoost. We are using the early science data of the cosmos field, and I'm sure you heard a lot about the mighty cosmos, so I'll just jump this. So it's a multi-wavelength catalog that we're using, and it compromises. It has emissions from the radio, optical, mid-infrared, far-infrared, and X-ray. And this catalog is already classified by Whittam et al. 2022, and about 33 sources are classified as AGN, 15% are classified as star-forming galaxies. We have about 40% which is classified as probable SFGs, and 12% which is not classified according to their conventional techniques. We then, from the catalog, derived the input features that we're going to use to train our machine learning algorithms. And we have M star, which is the total stellar mass. I should mention that in the figure on the left, I show the completeness of each attribute that we're using for training machine learning algorithms. And then, as I said, M star is just the total stellar mass. Plus star is an optical indicator that is used in literature to classify if a source is an optical AGN or not. We have the QIR, which is the infrared to radio correlation. We have class labels, which just indicate which source is active galactic nuclei or star-forming galaxies. And we then derive the 3 array colors. Now that we have features, and this is a low-dimensional feature space, you can then try to see how the two classes are distributed in each attribute or in each feature. And my favorite is the QIR, where you can see that the mean of the two populations is very different. So at some point you can estimate that below 2 you have AGN, and above 2 you have star-forming galaxies. In an ideal case, you will want the two classes to be as separate as possible so that you will have a clean clean way to distinguish between the two. Another thing is you can try to do feature analysis using automated techniques. And on the left, I show the ROC curve with some fancy terms on the vertical and horizontal axis. But the most important thing is your feature is very important when it has more area under the curve, and you can see that in this case, QIR which is shown in green, has more area under the curve. In the same way, we adopt another method called permutation feature importance, and you can see in the same way QIR is ranked as the most important feature. And I should mention that in this case, they are not dependent on machine learning or any algorithms, and then we confirmed with random forest results, and then you can see still QIR is ranked as the most important feature. And then we then decided to group features in terms of their importance. Before, when we train our algorithms, you can see we have F1, which is QIR, because QR is the most important feature. F2 is the two most important features. F3 is three most important features up to F6. And in F7, we decided to drop the two mid-infrared colors because the flux density coming from channel 4 and channel 3 of the IREC will not be having measurements in the near future. So what we want to do is we want to drop the colors that involve those flux densities so that you can see that how well your algorithm can perform even when you don't have those measurements. On the plots here, I show the results of 5 algorithms. On the vertical axis, I show F1 score, which is the scoring metric. And if F1 score is 1, it will mean you will reproduce good classification, then the algorithms are doing very well. And I should also mention that in this, we took 80% of the data to train the models and 20% to evaluate the algorithms. I showed the results for logistic regression in blue and K nearest neighbor in green, the support vector machine in orange, and random forest in red, XGBoost in magenta. And you can see that in all feature combinations, I have scores that are above 90%, which is good. We then try to do this for other splits where we use 60%, 40%, and 20% as a training data set. And you can see that even when we're using 20% as a training data, we still need a good score, where each and every algorithm still has scores that are above 90. And this is good because in the near future, the fraction of data that we'll have will be very high compared to what we currently have. And as such, if we can still yield good scores while we train algorithms in a small amount of data, then it's good for the future. And I'll just stop here. Thank you.
Yeah, go ahead.
I actually enjoyed your presentation. Thank you. I just had a question as to what informed your decision making in choosing those specific ML algorithms, such as your KNNs and your XGBoost?
What to choose the algorithms?
Yes.
So I think with logistic regression is the simplest algorithm that you can interpret. So you want to always try with things that you can interpret. And then XGBoost and random forest, they are just the best algorithms in literature. And so the other two, even KNN and support vector machines, they are still good in literature. But the idea is they all use different approach to find the relationship between the data and the labels. So yeah, I think that's it.
Because with the work you're doing, adopting deep learning ML algorithms is actually going better.
So yeah, with the deep learning, those are very complex algorithms. and I think I will just need to try and see how well it can do compared to these ones. But
I think you guys can discuss this.
okay.
So final speaker for the session.